Okay, welcome to Composability. We're going to start off with Ogas and Richard telling us about the custom ops and user-defined Triton kernels stuff.
Oh,
Okay,
so I'm
so
gonna
yes,
summarize.
sure. Let me
Okay.
like there are a lot of people here, so let me give a bit of a overview of like what is user-defined Triton kernel and I guess how they relate to custom ops. In the I guess most simplest sense, if you have like a Triton kernel that you wrote by hand, not an inductor emitted one, the user-defined Triton kernel feature now allows you to actually call this kernel from your PT to compile code, and this allows being able to compose it with many like few other features like I don't know, autograd, AOT inductor, JIT inductor, and dynamic shapes. So we have been thinking about releasing this for the PyTorch 2.3 release. However, recently we're also discussing about whether we should be combining, like packaging this up with custom ops or not. The main reason is that when you use the Triton kernels on their own as in their raw form, they're composable with the features I've listed previously. However, we don't really have a good way of composing them with some of the more like I guess fine-grained features, similar to like tensor subclasses, nested tensors, and similar features. So recently we have been talking about whether we should actually hold off the announcement of the raw user-defined Triton kernels for PyTorch 2.3 and package them along with the custom ops that will be shipped after sometime between 2.3 and 2.4. I guess, Richard, do you want to explain a bit more into the custom op part?
Yeah, so to clarify, there are like two main questions here. So the first one is like, what is the user story behind custom ops and Triton kernels? Like, do they go through the same mechanisms? Like, do we have two separate APIs to build on top of them? That's the first question. And the second question is like, given whatever user story we come up with, like what makes sense as like what we are going to announce?
Yeah. I guess talk a bit more about like the pros and cons. Internally we also start using the raw kernels for some of our workloads, and the reason is that with the raw kernels you don't actually have to modify your eager code, and whatever code you can run in eager you can also run in compiled version, which gives a pretty flexible user experience. Having said that, the lack of composability into tensor subclasses and few other features makes it slightly more challenging for an open source user to adopt this without having the support of a PyTorch engineer. Um, New York, I think you have your hand up.
Yes. In terms of features not supported, is AutoGrad and training in general not supported as well?
So AutoGrad is actually supported. We do support like function at AutoGrad both for training and inference. The particular thing that's not supported is I think, tensor subclasses. Is there anything else I'm missing, Richard?
It's tensor subclasses and it's whatever is in the PyTorch dispatcher. So things like make FX tracing, pre-dispatch export. If you wanted to specify an autocast role for your Triton kernels, you cannot do any of that today without putting them into a custom op.
And the AutoGrad support is done through custom function, I guess?
The autograd support is done through torch.autograd.function, which has its own limitations, but that's a different story.
Right. Okay. So
Yeah.
the benefit of being inline is not true for if you want AutoGrad support. You need to add the whole custom AutoGrad function on top of it.
So for AutoGrad, if you just write it in your backwards pass, it will work alongside with AutoGrad. You don't need to change anything from your regular AutoGrad.function, if that's what you're asking.
Right. So you need, yes. That my question was, do you need a custom AutoGrad function? Because I would expect this is as much boilerplate as a custom op, more or less, basically.
I'm curious, like, is there anything actually coupling? Because like basically like everything you said should just apply to all custom ops. So is this just like an instance of custom ops, and like once we fix custom ops, it'll fix this without any extra work? Or is there actually any coupling between the Triton ops and custom ops?
So ideally, like there's so one like philosophy is that there's like one way to do custom ops in PyTorch. If we put Triton kernels into this philosophy, then like you basically have a Triton kernel, you wrap it with a custom op to add functionality for other PyTorch subsystems. In that sense, like there's nothing really coupling the two. The thing that it gets complicated is when people have a Triton op and they use torch.autograd that function instead of a custom op. And then like to actually turn this thing into a custom op, you need to remove the torch.autograd function and then put a custom op wrapper around the Triton kernel.
But like if I write like a custom op in CUDA, like the way I'd make it work today would be I'd throw it in an autograd function.
Oh no, that doesn't work. You actually have to have a custom op, use a custom op around the custom CUDA kernel you wrote, because it doesn't have a meta kernel associated with it. And to be able to define a meta kernel, you need a custom op and not autograd that function.
I see.
Yeah, I think the main thing interesting here is that like are the raw kernels valuable enough without the composability into the tensor subclasses, or is it something that we should promote to only be used with, or like primarily be used with custom ops here? And then there's also a question of timing, but we can postpone the like discussing that.
Tris?
Wait, Richard, is what you're saying? I think the standard workflow for Triton, specifically for training, is you have a torch.autograd function, you put it in there, you call your things. You're saying that if you compile that, that won't work?
It does work, but if you want to like bring like nested tensor or detensor to this, like we don't know how to do it.
Okay, it's only
to
that.
use nested tensor.
That makes sense. Sorry. Yeah.
I think I'm pretty sympathetic to the idea that like you should just always use custom ops for this, because like otherwise, like, you know, if we are supporting raw kernels, then what this means is that you have one kind of workflow that works purely for like Triton kernels, and you have one workflow that works that you need to do if you use CUDA kernels, and these are like kind of separate paths that work for Triton kernels and CUDA kernels. And this seems kind of strange to me. Like, to me, I feel like perhaps a better option actually, no, I just think custom ops are probably better here to use. Because like if you're using it in training, then the option is basically just like autograd function and Triton kernels, or custom ops and Triton kernels. And I feel like it's better to just unify on custom ops and Triton kernels. I think one thing we could do is we could probably make it so like if they are doing raw kernels purely in inference, like, or we can like minimize like the syntactic overhead of doing it. But I do think there's value in unifying on like the custom ops stuff.
NYC Chalet?
Yeah, I would definitely agree with you on that. I think from my point of view, to a large sense, the recommendation we'll have once custom op is out is you should not use custom autograph functions anymore, unless you need the flexibility of having very specific non-dispatcher object going through. And so I think all autograph overrides should go through custom ops going forward. Greg, I think you were next.
Can people hear me?
Yes, now we can.
Okay. Does whatever we're doing for like the Triton parsing allow us to like interject, like if you try to run this thing through AutoGrad, we can give you an error that says like do it in a custom op.
So I think we discussed this in the past, and we can add a special check to do this. I think there was a question around like how many things should be like special case there. I think currently it will fail with just trying to run it with fake tensors, which is of course not something you can do.
A Triton kernel will actually set called if you run it through fake tensors. I actually talked to Boris a bit about this, and we were thinking of if we could add a hook into the Triton API that lets us just like hook something like a torch function handler. It lets us do something when Triton kernel gets called. If that happens, then yes, we can actually like raise nice errors or actually handle them.
Yeah, I talked to like Karen, who's like a Triton dev, about this, and he thinks it's pretty reasonable to do something like this, and to have a like hook in the place where we want there to be a hook. So yeah, I think we can do it. I think we just need to like write a proposal and then submit a PR upstream.
Okay, so since there are no hands, does anyone want to advocate the opposite, which is that we should just release Triton user kernels as is and tell everyone to use them?
My only reason is that like they provide quite a strong use case on their own, but I'm not like that. Like I'm perfectly fine with not doing that for external. I think for internal this is definitely something we need, but for external we can definitely do a larger thing around custom ops.
Horace?
Uh, I actually do think there's value in just releasing Triton kernels support as is. But I don't really know how to reconcile it. Like my I guess
I mean, you
feeling
can
here
just
is
release it and then like mention it in the release notes and then not be like, oh, you should use this, sound it from the rooftops. Like I think there's a gradient here.
Yeah.
At least like from the like the GitHub issues we are seeing, there are quite a few people who are discovering this feature during on the nightlies and already start using it.
Sorry.
So
I think I have a proposal that I feel like makes sense to me. Like I think the really big problem with Triton kernels today is that they will crash and do not like things if you're passing them a non-tensor. So like if you're passing them like a tensor subclass, they're just gonna crash, right, or segfault today. And so I think that's why we are a little bit hesitant about like promoting people just directly putting Triton kernels into their code. But I think if we can like have if we can prevent this and we can direct people towards the custom ops API when they're using Triton kernels in a way that doesn't work, I think that would be pretty reasonable. I think like if we can do that, I would be fine with like releasing the Triton kernels as is today. Simply because I think there is value in kind of having like the minimal syntactic overhead to like integrate a Triton kernel into your program.
NYC?
Yeah, I think I'm definitely not arguing there is no value in this feature. I think it's super useful. But I think the main thing I expect to get by adding custom up on top of it is safety. Is like custom up gives enough structure around the kernel that we can actually guarantee that different subsystems will work and end users will be able to reliably use this feature.
Yeah.
And I think in internal, both internally and externally.
Yeah, so I'm proposing that we need to add like a hook into Triton that allows us to error upon like people using it unsafely, which I think or like at least from thinking about it right now, I think like the hook that Richard mentioned earlier is sufficient, where we check on the tensor subclassness of inputs going into a Triton kernel. And I think that is also sufficient to allow for safety in cases that people are using subsystems with raw Triton kernels.
Yeah, I think as long as you don't have silent correctness issue or hard crash, when people use it in usual ways, then I think it's fine to release as a feature. And I don't know if you can get that out of the box or if you necessarily need custom ops to give you these guarantees.
Jansel?
Yeah, I think we should release it as is, and there's sort of like a few pieces with that. Like one is like people already in eager mode are writing custom Triton ops, and they're working today. And so it's not the case that this is like actually like an unreleased thing. This is something that like you've been able to do in PyTorch for the past year in eager mode and the past few months in compile. And like there's lots of legacy code out there that uses Triton sort of the way Triton tells you to use it on the Triton website. And like that code, that like we shouldn't like break that code and say like no, like the way you've been using Triton for the last year, like we're going to take that away from you. So in some sense, like there's this new API coming, and it's not there yet. It's not ready. Like people can't like we can't like credibly tell people who are using Triton in Eager today, like, yes, like the custom op is ready, like go use it. This has been a feature that we've sort of been talking about building for the past 6 months. It's still not here. It's still not ready. Once it is, like, once there actually is a better solution, we can like start publicizing, like, hey, like there's this better API. Here's the advantage of this API. We can ask people to migrate. I also like Horace's idea of like detecting when the old API is used unsafely, and then like having an error message that like links to the doc explaining the new API. I think the like way Triton is used today is not something we can like roll back. Like it's the API of Triton.
Yeah, I also like, generally speaking, like one API thing I don't like is when something breaks for some use case and there's no good reason why it has to break. Like, like if it just errors because like, they're passing in a tensor subclass and it says blah blah, we can't support this, you need to register something. I think this is something that users understand. They're like, okay, yeah, that makes sense. I need to register something that allows me to do something else when like special behavior is required. But in this case, like if they're just using raw Triton kernels in inference, which is like a pretty common use case for raw Triton kernels, I feel like it's pretty strange to just say like, no, we don't you can't do this, even though it works today, and there's no, like, we could support it.
Okay. Alban,
Sorry. Yeah, just to clarify, I was definitely not suggesting we break what we have today or we limit what we can do today in any way.
Okay, so I want to summarize. I want to summarize the discussion. Yeah. So it sounds like a few things. So one is that we should have an error message that points people at the custom ops API when they try to backprop through Triton kernel that otherwise isn't. Richard, I think you're the logical person to implement this. Does that make sense?
Sure. Yeah.
Okay. Part 2 is we need to make Triton stop crashing when you pass it fake tensors. I'm actually a little confused why we don't just raise an exception when you access the data pointer on a fake tensor. Maybe we can actually do this.
We cannot. Well, we need to add a check into data pointer, which is potentially slow, which is why I haven't. I want to do this before, but like.
I think you have a lot more play here. In particular, you can put the check only in the Python binding and not in the C++ binding, unless you're telling me that Triton is accessing data pointer from C++.
It should be accessing it from Python, but also like fake tensor is a separate class, so we can just define the method.
Yeah, you can just define a method, exactly.
Yeah.
Like it doesn't. We don't even need to touch the regular bindings.
Part 3 is we are not going to do something like add a feature flag that you have to turn on to enable compile with Triton kernels. I think we resolved that. I don't know if I think it would be wrong to not include it in the release notes. If you guys want to duke it out about whether or not it goes in the blog post or not.
I think we should.
Should go in the blog post.
As long as we can avoid like, I think, hard crashes. I think ideally we should be able to point people towards custom ops. Like in the cases where it would be useful. So like not seg faulting on data pointer access is one thing. But I think ideally we do want to like upstream a hook into Triton that allows us to like tell people like what tensor subclass are passed in and say, use the custom ops API or something like that.
Okay, but Horace, would it like harm you deeply if instead of putting it in the release blog, we put it in a separate blog that happened when we actually had fixed that thing and had the custom ops docs ready to go?
I guess no. I don't.
It makes sense to just announce it with the current limitation, with current, like, also the exceptions around it, and then to later, like when custom ops are released, actually promote it to be used along with custom ops. So this way, like, it would give the engineers the option to choose whichever they find better fit for their use case. And if we get a lot of complaints on issues, we can point them towards custom ops at the time.
I just want to check is.
I also say like we shouldn't be pushing people to rewrite code that works fine today for no reason, right? Like,
Or, no, I think we're all in agreement that we will continue to support, or sorry, I don't know if we're all in agreement, but I think the tentative agreement we came to is that we're going to support raw Triton kernels in the way that they're used today.
Yeah, but when we make that post, when we like announce that, like, hey, like we have this new feature, like it should not be like hey, like we rewrote autograd function, like autograd function is deprecated, like go proactively rewrite all your autograd function usage to use this. It should be like hey, this new API supports these features, and if you need these features, you should upgrade. And it should be sort of like there should be a carrot there. It shouldn't just be like we broadcast the community, hey, you rewrite this, we've just made work for you. It should be adding value to the users.
Richard.
Yeah, so I don't think it's that simple. If people just write autograd functions today, it provides a maintenance burden for whoever comes along in the future and wants them to use them with new features. We see this with custom ops in FB code. If they use autograd function, they use it in the wrong way to actually support custom ops. So someone else who didn't actually write the code, someone else who has no clue what the code is doing and who also doesn't know about how PyTorch works, actually does the work of rewriting it. Or they actually can. And so like one of us needs to step in and actually help them do that rewrite. So in that case, like I think I would actually recommend that people, like if they own some code, to actually rewrite it in this new format so it's easier for new code to build on top of it.
Greg?
For the release blog, we can be clear about the limitations, right? And just say like, just use this for inference, basically. Is that correct? Like, if so, I think that's totally fine to not have to wait.
Okay, I want to amplify Richard's point just now a little bit, which is that like it is not free to go from the plain eager code to then autograd function, because then if you end up needing the extra feature later, you have to then do another rewrite again, which Richard is telling us that empirically this is actually pretty difficult to do, and I believe him because I've also looked at some cases of having to do this port. So, like, the thing is that people are just going to like slap autograd functions on no matter what we write in the docs. So I would like to bias towards Richard's perspective in the docs we write, because like people are still going to do whatever. And so like, absent hard enforcement, which I think the room has agreed we are not going to do hard enforcement. Like basically we should give Richard everything he wants, because like, as I said, people are just going to do whatever. Like, he's kind of like on the wrong side of the foot in some sense. Jansel.
I mean, but by that logic, every time you use autograd function, it should throw a deprecated warning. Which, maybe we'll reach the point there, but I think we should build the new API, make sure the API is like good and working. I think it's too early to I think it's way too early to be deprecating autograd function, and people are going to continue using autograd function.
I think there are two steps here. I think there is a step of we recommend people use custom ops for the case that custom ops supports. But I'm definitely not against the idea of saying like in 1 year, custom autograd function should be deprecated, because we consider that custom ops are the way to go, and we want to force more people to go there, because otherwise they always end up doing this two-hop thing of like they write a custom autograd function, it works for a bunch of stuff, and then they hit torch compile, and then they have to rewrite it again to use custom ops.
And Alvin, just to clarify what you mean, so when you say deprecate, does that mean you would eventually remove it, or you would stop with the deprecation warning?
I don't think we can completely remove it due to the fact that things like torch bind are not mature enough as of today. If we can lift this constraint that we have, that you need a schema that goes through the dispatcher for custom ops, or like if we can make the dispatcher flexible enough that anything can really go through, then I think we can actually deprecate and remove it. Yes.
Just.
I was essentially going to say the exact same thing. I feel like going to the dispatcher is a much more of a filter for custom ops than AutoGrad design. AutoGrad function.
Richard?
Read my filter.
I mean, like, I think it's much like that. Like, one added restriction is a big restriction in my mind.
Sure. I don't think we'll ever be able to remove AutoGrad function because it lets you do some crazy stuff in Python that people do rely on. So we'll never actually deprecate it. It's more that like we will like when we do custom ops like blog posts, we will just recommend that people use this for things that involve custom ops.
Okay, I actually want to resolve this disagreement. And Albin, I'm going to disagree with you. I don't think we're deleting AutoGrad function. I think the most we will do is make it emit a deprecation warning forever. But I seriously don't like see a way, like practically speaking, of actually deleting it.
Not for the next few years. Yes, I agree.
Well, that's basically never. Like we can have another discussion at Composability 5 years from now when we actually can do this. Greg, I don't know if you wanted to talk or not.
I was going to say we have prior art with torch.capital T tensor, which sucks. But we're never going to remove it.
Well, we also have prior art for all style custom AutoGrad functions that we actually removed from the code base.
We removed those.
So we already did a transition from old style to new style.
But we removed those at like 0.2 or 0.3 back before PyTorch was really, really popular.
Okay, so with this established, then
yeah, so my pitch was like in custom ops messaging and Triton kernel messaging, when the custom ops APIs are ready, like we suggest them to use the custom ops to do AutoGrad. Instead of AutoGrad function, we won't actually deprecate AutoGrad function, but we will recommend it wherever we can so people can actually pick it up.
So what I'd be comfortable is I'd say we should recommend that new code be written with AutoGrad.function. And maybe we want to start like a migration effort inside of FB code. But like I don't think we should be making a post.
To be clear, we are already doing this in FB code. So like, you know, when we're talking about meta policy, we could consider just banning AutoGrad function outright in meta.
Yeah, I'm fine banning it in FB code. Like that's something we control, right? But there's like, you know, a lot of code out in the wild is like really old, it's really long lived, and it may never ever try to work with like tensor subclasses or these types of features. And so I think it's like it's safe to say sort of like we recommend this for new stuff. You know, obviously once it's stable, like maybe they'll take some iteration where we actually want this to be a beta feature for a while, and while it's a beta feature, maybe we don't want to be pushing people to migrate as hard. But you know, like sort of, I think there's sort of the step of saying, okay, we recommend this for new code, but like, you know, we're not sort of doing this massive migration where we're asking like everyone to rewrite their PyTorch models in sort of a big transition push. I don't think that's a net win for most people.
Sure. I think we would not tell people to go out rewrite all of your code unless it's been like a couple years down the line. But we can start with saying that like, hey, your new code should be written like this. / saying that in a docs as well.
So is the plan for this feature to go directly to stable without a beta period?
I don't think the beta stable distinction actually matters here. Like we're going to release it, people are going to use it, we will maintain BC for it as much as we can as a normal feature.
We already have internal customers using it, so it is somewhat battle tested.
So sorry, Jason's ask is for custom ops.
I'm asking. I'm not asking about Triton ops. I'm asking about custom ops. I'm saying.
I think a different way to pose Jason's question is, Richard, do you want to give yourself like maybe a month or two of, oops, we need to make this BC breaking change because it's important?
Yeah, so my plan is to like release this thing in a night release at the start of like right after the 2.3 branch cut, and then like have that time until the next release to actually refine the API.
And stable immediately at the main release.
We can start with beta. Like I don't think the designation actually matters.
It matters if you're going to do a public release and then do a BC break on the next release.
Okay.
Yeah, I guess Ed sort of correctly articulated my concern, right? This is a new API. It doesn't exist yet. There's a lot of subtleties in it. Like we've been talking about it for a long time. And, are we going to get it perfect the first time? Probably not. Like there's probably going to be some things that we didn't think of. And it might take some iteration to really get it right. And like if we immediately go out and say this is stable, it's BC, we make a big push to get everyone to use it, then we're locking ourselves in and basically saying, okay, like any mistakes that we made in the first version we're stuck with forever.
Yeah, so this is my third time actually writing this API. I've had 2 previous drafts. In terms of just my point with the beta versus stable distinction is even if we release this as beta, I'm maintaining BC for it. Because my experience is people are going to jump on this immediately and we cannot change anything. So, but we can release it as beta first if the terminology makes us happier.
No.
But like,
so the question is, are you going to BC break it after it gets into the release? And the answer is
I'm not going to BC break it, like as much as I can.
And I'm willing to take Richard's word on this because indeed, this is, we have released multiple versions of the custom op API before. So it's not like this is coming out of nowhere. Like we actually do have a lot of experience on this. It's like
So I'm not going to BC break it, but I'm happy to label as beta to make ourselves feel better about if we need to BC break it.
Okay, I'm satisfied with the outcome. Does everyone any last concerns, questions?
So I guess for my clarity, I will still proceed towards announcing this for.
Yeah, you can put it in the blog and work with Richard so that Richard's happy with the disclaimers section.
Okay, that sounds good.
I think my hard line is like no segfaults.
To be clear, I don't think even if you use fake tensor, it doesn't segfault. It just like has an assertion failure, but that might just be as equally bad. Who knows?
Segfault is worse than Python exception.
Okay, Triton has some thing that checks whether something is a CUDA tensor, and at that point it will just assertion failure.
How does it tell? Like device equals CUDA. Fake tensor is supposed to act like a CUDA tensor. Like you can't tell without looking at the type or the data.
Yeah, I didn't dig deep into how Triton does it, but we should probably just error inside PyTorch rather than let Triton deal with this later.
So, under the hood, Triton is only reading the .data pointer on the .d type. And it doesn't actually even check the device for that assert. It's actually probably looking at like the where the data pointer is pointing in memory and doing some checks based on that. And the reason why Triton's designed that way is that you can also pass Triton a like fake placeholder tensor that's not a PyTorch tensor, and that fake placeholder tensor only has those 2 methods on it. It doesn't have anything.
Okay, so I heard 2 things. So like 1, yes, blog post, however we like. We can discuss like exact wording, and then 2, we should have like hook into Triton for safety. Do we care about that at all, like right now, or like is it okay for this to come later? Or
someone should just write the data pointer method on fake tensor and see if we can land that. And we can land that, we should just land that.
Yeah. Also, even if we do write it in the Triton, we would have to wait for the Triton updates. So that will probably be more time duration.
Okay, so it sounds like just try to make sure fake tensor doesn't segfault. It sounds like it might not already, and then we're good.
I will share the current behavior into the composability group.
Okay, done and dusted. So no one voted for anything else. So Ogas, you get to pitch us FXIR C++. You don't have to take up all the time. I know you're still planning it out, but just like the general broad strokes of what you want to do.
Okay. Yeah, so this is like just a very rough sketch. So over I guess lunch, like Horace and I were talking about, should we be actually rewriting the FX graph in C++ so that we will be able to like just do the operations over it faster than what we would be able to do in Python. This also goes kind of hand to hand with our like policy of it's okay to rewrite like subcomponents that are needed for performance. There are a few things that are kind of interesting to talk about. Um, as with like Python's own language, it's often that people interject properties into the FX graph that are not actually on the FX graph originally, like dynamically injecting it. This poses a bit of a problem because it makes it harder to actually performantly do this by like writing the C++ version. However, this actually doesn't happen inside in PT2 as much as it does in the regular FX. So this kind of brings up the trade-off between should we actually have like one C++ FXRef implementation that we use in everywhere in PyTorch, including like PT2 and the rest of PyTorch, versus should we actually and doing this would require us to support this like dynamically interjecting new properties into nodes, or should we have parallel implementations, one we use for compatibility and one we use for performance? Ed?
So my take is there are plenty of occurrences where people have taken Python modules and rewritten them in C and kept both because it's helpful to have a Python reference around. But the C implementation always had feature parity with the Python one. And I think that's the goal you should aspire to in this situation.
Okay, I guess I'm not as familiar. Is it in these cases like, do the C implementations actually support the dynamic injections, or?
I mean, so obviously there's some stuff that is private and therefore like not, considered part of the API surface that you have to support. But like once you define the public-private split, then, yes, they should support all of the public API. Horace.
Yeah, I think it's unlikely to rewrite it or like to completely replace our current Python implementation with the C++ one. I'm pretty sure people, sorry, I'm pretty sure I literally do this in like the partitioner. I just assign random attributes to the node. And I'm pretty sure people do this all over the place within Epi code as well. So and I feel like it's a bit unlikely, although like to do it, although perhaps there's a way to support it.
So?
You're muted.
You can't hear me?
Now we
Yes.
can.
Okay, right. Okay. I don't know. Zoom. I think it's a good idea. I think for various reasons, I am supportive of more like native implementations, especially in core infrastructural bits. I know, for example, for like the Edge team, like just FX Python munging is like a significant part of total export time. I kind of agree with what everyone said. Every time we try to tighten up even like a small invariant about FX, it like breaks a billion things. I do think like one thing that we should kind of explicitly do is define a more structured, like pedantic subset and require that PT2, like our first party infrastructure, conform to the more pedantic subset. And then, whether or not random users writing FX passes like have to conform is TBD. Maybe one day we'll go after them. Maybe we won't. I don't know. Does that make sense as a basic like principle? Because if we say it has to have feature parity, it's just not going to work, right? Because there's too much shit that people do with FX passes.
So concretely, Michael, you're proposing that we fork FX and have a PT2 internal version that is fast and C++.
I don't know if it's like fork. Like I said, I think subset.
I mean, there's going to be two copies of the code. They're going to have, different, well, maybe they'll have exactly the same semantics, but one of them is a subset of the other. Sure sounds like forking FX to me.
Well, I mean, I think it's broadly defined. If the goal is to replace FX, like be a wholesale replacement for FX in C++, it's just not going to happen, right? So I think if we want to have like a native medium to do some of this pass writing, that's like a little bit faster or whatever, like, you know, you either have to fork and we should be like clear that we're paying that cost, or we shouldn't do it.
Elias?
It'd be like, you know, it's gonna make ergonomics worse. And it'd be great to have some like benchmarks and justification for how much it's actually gonna make things faster. Because if it's like 2 or 3 seconds, like I think there's a you know, a number of other things we could do in that same time to improve compile time without sacrificing ergonomics. And I don't know, once we start like this rabbit hole of like moving small pieces into C++, like maybe in the short term we'll get some wins, but in the long term we're going to be like moving more slowly. And I don't know, I'm skeptical, I guess.
Chancel?
Yeah, I'm skeptical as well, and part of that is that I think that at least today, some of like the most complex and sort of like Python magic-y usages of FX are actually in PT2. So like I think so like the story of like, oh, like people can do weird Python-y stuff in the wild, but then in PT2 we need to like be conformed. That's sort of the opposite of what we have today. Like we have like, you know, we have tons of places in you know, Dynamo where we're like just shoving Python lambdas in there and setting arbitrary attributes and like that like maybe we could rewrite everything to like not do that, but that's not something like I think we should make high priority. I think like if like the goal here is reduce compile time, I actually think there's like a much more narrow thing we could do, which is if you do some profiling of FX, one of the most there's a few things that are very expensive in FX. So one is recompiling FX graphs, basically where we generate a big Python string, we exec that Python string, is enormously expensive. And actually Shunting did some rewrites where he'd do that lazily to try, because what we do is we generate this Python string, we'd exec it, and then we'd never actually use it. And like that was just really, really slow. And so I think what we could do is we could do something where we could say, we're going to change the way FX generates, FX works. So rather than generating a Python string, we have a C implementation which basically interprets the FX graph without actually cogenning Python and compiling it. And I think that would help compile time a lot. The other thing we have is throughout the compiler, you can sort of, what really starts adding up is number of passes over the FX graph. So like a lot of FX passes are written where you iterate over the entire FX graph to check for a single op, then you iterate over the FX graph again to check for a different op. And like you end up having like, you can sort of like measure compile time and like how many times do we iterate over the entire FX graph. And so there's like a few ways we can improve that. Sort of one is like better pass infra, so we could basically combine passes over the FX graph and do fewer passes. The other thing we could do is we could maintain data structures on the side of FX that allow you to very efficiently check, does this graph contain any copy underscores? And if the graph doesn't contain any copy underscores, I don't need to take a pass over the entire like thousands of nodes in the graph to check for any copy underscores. And so we can basically like start gating a lot of our passes based on like really efficient checks for does the graph contain X? And we can implement those in C++, but we can also implement those in Python, where like, you know, the FX infrastructure has a lot of stuff to like keep track of like predecessors and successors and node counts and stuff like that. And we also do some things like keep track of, you know, all the ops contained in this graph, and that would allow us to really efficiently skip entire passes over FX.
Okay, August, what are your thoughts?
Yeah, I think like based on the usability argument, by that I don't think we need to actually rewrite it in C++ entirely for the usability aspect. And also if PT2 is actually using it quite a bit more than like quite a bit intrusive ways than regular like vanilla Python, then yeah, this would completely defeat the compile time argument anyway. I'm happy to look into the suggestions you made with like serialization or like the site tables. with combining the passes, I do worry that that will also be a usability hit, because then if things are happening in parallel, it might be unclear like what happens after individual passes.
Yeah, I agree with that. There's, we need the right infra so that you can like declare your like multi-classes in a clean way. We can make sure they don't conflict with each other. Like basically, we'd have to build up some compiler infra such that we could be more efficient about how many times we iterate over the entire FX graph. I mean, the other thing is like there's just a lot of cases where we're iterating over the entire FX graph for basically no reason. Like I was looking at some of the partitioner code, and in the partitioner code, I believe we made 5 passes over the FX graph, and all of those 5 passes were just to check for placeholders. So basically, and we know all the placeholders are at the top of the graph. So basically, like in order to figure out how many inputs.
I don't think that's quite accurate in this case. Like the particular, I know which one's you're referring to. It is specific related to the specific way you construct the graph. And we are like constructing, like we're not doing like 5 passes of the graph. We're doing 5 like reconstructions of the graph.
So this is literally like there's this thing where I can link you to the code because I actually have a fix for this already. But it was just to find the placeholders. So it was basically saying, there was basically like 5 list comprehensions where we iterated over every single node, and we said like, is the node a placeholder and is it a tensor? Is the node a placeholder and is it an X? And so it's like completely dumb that we were iterating over every single node in order to find the placeholders.
I don't think that's like the main usage of compile time in the partition.
I know, and I'm just mentioning that like. We just take passes over every single node in the graph over and over and over again for no reason.
Michael Swell?
Yeah, I think like this could benefit from a lot of data, like things that I would love to understand more deeply. One is like, how weird are we in PT2 with stuff? Like that's something that like, is that super expensive to rewrite? Is that a thing where like, I mean, C++ doesn't stop you from attaching Python state to things. Like this is not that bad, right? Like the second is how intrusive would the infrastructural changes need to be to like make things fast? Like I do worry that we're going to spend a bunch of time like crafting things to make it faster, and then it's going to decay again as we add more passes or whatever. Meanwhile, each individual pass is like 100x slower than it should be because it's written in Python. Like that's the kind of thing that I don't want to like. I'd love like a more thorough characterization of like how we use FX in PT2 to understand. Similarly, like if we have an elaborate pass infrastructure, we have all these extra data structures, like we would like to make assumptions about the graph. For example, it's not true that all placeholders have to be at the start of the graph. Like we just that kind of is true, but it's not like always true, nor is it true that like the output is the last element of the graph. I remember Oz tried to add a linter check for that and it exploded and we couldn't land it. So like to some extent, like at some point it turns into a fork because we're just like, hey, all the semantics of the graph are more nailed down and different so that we can be faster. Also, we have a completely different way of programming passes because we want it to be faster, etc. So I do wonder, like, yeah, what's the tipping point at which we're just like, hey, suck it up. We have to like just rewrite a new like thing because we want it to be fast and not. I don't know enough to like make a decision about that. So I guess my question is like, yeah, like what data can we gather concretely that would help us make a decision?
August? You're muted, August.
One thing I want to add to this is also like with the metadata or like the site tables, we will be able to improve the performance of the passes that we have in PT2 or like passes that we have control over. But like quite often we also see like passes in FP code that we don't really control as much. And like they also face the slowdowns due to the FX traversing. And unless like we also expose our metadata to them and like ask these people to start using the metadata to improve